Sometimes when we're approaching an integral and it's not obvious how to proceed, when we're in the multivariable context, reversing the order of computing the integral can help. For example, for this integral, which is the outer integral is the integral from 0 to 1 in y, and the inner integral is the integral from square root of y to 1 with x. So we're trying to integrate this integrand, the square root of 2 plus x cubed, and we're trying to integrate it dx, and this just looks hard. Like there's not an obvious u substitution that we can do to simplify this, because if we somehow substituted for an x cubed, we'd want a 3x squared floating around, and we don't have one. So not obvious how to approach this at all, and in this kind of case, one of the things that we often try first is reversing the order of integration. To begin to reverse the order, we need to start by sketching the region of integration, because we need to switch from horizontal stripes to vertical stripes, or from vertical stripes to horizontal stripes. And to do that, we need to know what the region is that we're working with. To find the region, I start by rewriting the bounds. And I'm going to rewrite the bounds really explicitly as y equals 0 to 1, x equals square root of y to 1, and then my integrand doesn't really matter for drawing the region, dx, dy. So to write these bounds, I said, dy was my outer integral, and so these bounds actually mean y equals 0 and y equals 1. Dx was my inner integral, so these bounds actually mean x equals y and x equals 1. Now that I've rewritten the bounds in this way, I can make a sketch. Because the outer bounds are always just numbers, they're usually quite straightforward to sketch. And so here, let me put some axis labels on, x, y. So here we're going from y equals 0, that's a line along this axis, to y equals 1. A line up here, and I'm just going to make an arrow to remind myself that we're going from 0 to 1, that's what this order of the bounds means. Okay, and then next, the x bounds. So one of them is x equals 1. That's quite straightforward to draw. And that's the upper one, so we're going to be approaching it from this direction. And then the other one is x equals the square root of y. I don't actually necessarily know how to draw that off the top of my head, but I'm going to just solve for y, and I find y equals x squared. Okay, y equals x squared is definitely a curve I know how to draw. That's just a parabola, and it passes through 0, 0, and it passes through 1, 1, and it looks like this. And remembering that I'm going from this curve to that curve, I now am able to shade in the region of interest because I've had these arrows to remind me. Okay, so this is the region of interest for the integral. That's our region R. In my original integral, I was moving in x first and then in y. And so if I'm changing the order of integration, I'm going to move in y first and then in x. And when I move in y, I move from a lower limit to an upper limit. So in this case, the lower limit, at no matter what point in x I'm starting at, is definitely 0. So I'm going to draw my inner and outer, and it's going to be dy and then dx. And my integrand is unchanged, so it's still 2 plus x cubed. And now I'm going from y equals 0 up to this upper curve. And this curve was given to us as x equals root y, but we were able to rewrite that as y equals x squared, which is what we want now. We want these things to be in terms of y equals because of the dy there. And then for the outer integral, we need to know these intersection points because they create the outer bounds to determine where our shadow is of this region along the x-axis. And so these intersections are of y equals x squared and y equals 0. That happens at 0, 0. And y equals x squared intersecting x equals 1, which happens at 1, 1. So we have x equals 0 up to x equals 1. So these are our new bounds. We're going from y equals 0 to y equals x squared. And we're going, once we've found those sums, we have numbers at every point between 0 and 1 from doing this integral. And so we'll want to integrate from 0 to 1 to add all of those up. And now we're ready to do our first integral. The first integral that we're doing is the integral of the square root of 2 plus x cubed dy. But right now we're integrating in terms of y. And so when y is the variable of integration, we can just think of x as a constant. And so this whole expression is actually just a constant. And so when we integrate, we're just going to get a y because it's a constant times y. So we have the integral from 0 to 1. And then we have the square root of 2 plus x cubed, which was constant for the purpose of this integration, times y from y equals 0 to y equals x squared. And so plugging in the x squared and the 0, we get the integral from 0 to 1 of the square root of 2 plus x cubed times x squared minus 0. And this will all be integrated dx. Simplifying, we now have the integral from 0 to 1 of x squared square root of 2 plus x cubed dx. Note that in the bounds of the y integral, there could be x's, so there are new x's that were introduced into this integrand. And these new x's that were introduced help a lot, because now we actually can do a u substitution. If I let u equal x cubed, then du is 3x squared dx. And when the integral from x equals 0 to x equals 1 of x squared square root of 2 plus x cubed dx becomes the integral from u. When x is 0, 0 cubed is 0, so u is 0. And when x is 1, 1 cubed is 1, so u is 1. And then this square root of 2 plus x cubed becomes a square root of 2 plus u. And this x squared dx becomes a 1/3 du. So my new integral is the integral from u equals 0 to u equals 1 of the square root of 2 plus u 1/3 du. And this integral should be 2 plus u to the 3/2 times 2/3 times that initial 1/3 with u going from 0 to 1. And if we take a look at this, if we were to take the derivative of 2 plus u to the 3/2 times 2/3, that 3/2 comes down and cancels with the 2/3, and we would get 2 plus u to the 1/2, which is exactly what we wanted, so that checks out. And now I just need to substitute in those 2 points. And so this is equal to 3 to the 3/2 times 2/9 minus 2 to the 3/2 times 2/9. So I'm just going to write that as 2/9 times 3√3 minus 2√2. Okay, and so that's my final answer to this integral. What was our overall method for this problem? We were given an integral of this form where we were integrating using horizontal stripes. We started with the horizontal integral in x, and we weren't able to approach that integral. So we drew the region of integration by rewriting this as x equals h1 of y, x equals h2 of y, y equals a, y equals b, and sketching the region associated with that. And then we turned it into an integral that was in the order of dy and then dx. So we turned it from a horizontal stripe integral into a vertical stripe integral, and then we were able to evaluate it.